something is amiss in our comprehension of the universe. Cosmology is advancing toward an essential junction, grappling with what may be one of its most significant issues. How quickly is the universe growing? For over 10 years, two different measurement techniques have been at odds. Observations of the current-day universe regularly show that the rate of expansion, known as the Hubble constant, is around 9% faster than what is anticipated based on data from the early universe. Experts had hoped that the James Webb Space Telescope, the most advanced telescope ever made, would help resolve this issue definitively. However, consensus has yet to emerge, as the telescope's exceptional and novel observations have further highlighted the disparity, posing a potential challenge to the established cosmological model. Now, the need for new physics to either modify or entirely replace the 40-year-old theory is under serious discussion. An exciting possibility is that we are overlooking some aspect of the universe. Join us as we dive into how the new ultra-deep images from James Webb have recently confirmed that there is something fundamentally flawed in our understanding of the cosmos. Our universe began with a bang, the Big Bang. Energy, mass, and space emerged in an instant. In the early moments, the young universe formed a seething plasma, a mixture of matter and antimatter particles that collided and annihilated each other. Left unchecked, the matter and antimatter in this plasma would have completely destroyed one another. However, scientists believe an unknown asymmetry allowed more matter to form than antimatter, thereby saving the universe from immediate obliteration. Gravity then compressed this plasma, heating it so intensely that sound waves, known as baryon acoustic oscillations, propagated through the medium at roughly half the speed of light. Simultaneously, the dense energy content of the early universe stretched space-time, pushing small pockets of matter safely away from the heat. As the universe expanded like a balloon, the standard narrative suggests that normal matter, which interacts with light, began to cluster around invisible dark matter, forming the first galaxies connected by a vast cosmic web. As the universe's structures spread out, its energy density, and therefore its expansion rate, declined. Yet, around 5 billion years ago, galaxies began retreating faster, driven by a mysterious force known as dark energy. The simplest and most widely accepted explanation for dark energy is that it functions as a cosmological constant, a uniform force that remains steady across both space and time. Woven into the fabric of expanding space-time, dark energy, labeled lambda by Einstein in his theory of general relativity, remains constant in density even as the universe grows. Eventually, dark energy became the dominant contributor to the universe's expansion. When combined with normal matter and dark matter, the energy densities of these components set an upper limit on the universe's expansion speed. These elements form the core of the lambda-cold dark matter, lambda CDM, model, which describes the universe's evolution and predicts its ultimate fate, a heat death known as the Big Freeze. Many of this model's predictions have proven remarkably accurate. However, this is where the problem begins. Despite extensive research, astronomers remain in the dark about the true nature of dark matter and dark energy. As A.F.R. Love, an astronomy professor at University College London involved in dark energy studies, states, most scientists agree that the universe's current composition is approximately 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing truth is that we still do not understand the latter two. A significantly greater challenge to the lambda CDM model, however, is the growing issue known as the Hubble tension. Depending on the method used, measurements of the universe's expansion rate yield conflicting results. The discrepancy is so significant that it has become a major issue in cosmology. Measurements based on observations of the early universe suggest it is expanding far faster than predicted by the lambda CDM model. These methods have undergone extensive testing and validation through various observations. As Nobel Prize-winning astrophysicist Adam Rees, who led the team responsible for the latest James Webb measurements, puts it, measuring the universe's expansion involves more than just using a radar gun. One primary method for assessing this rate examines the cosmic microwave background, CMB. the universe's first light emitted around 380,000 years after the Big Bang. This imprint is visible across the entire sky and has been mapped to determine the Hubble constant with less than 1% uncertainty. Between 2009 and 2013, the European Space Agency's Planck satellite produced a detailed map of the CMB. In this vast depiction, the universe appears nearly uniform, but slight temperature variations where matter is denser or sparser mark regions where baryon acoustic oscillations left their imprint. This soap bubble structure expanded into the cosmic web, a network of filaments connecting galaxies at their intersections. By studying these waves, cosmologists determine the quantities of ordinary matter, dark matter, and the cosmological constant, dark energy, calculating the Hubble constant to be about 67 kilometers per second per megaparsec. Let's pause to unpack this number. If a galaxy is 1 megaparsec away, it will recede at a speed of 67 kilometers per second. At a distance of 20 megaparsecs, this recession increases to 1,340 kilometers per second, continuing to grow with distance. If a galaxy is farther than 4,175 megaparsecs, it will recede faster than the speed of light. Another method to measure this expansion rate involves using standard candles, pulsating stars known as Cepheids. These stars' outer layers expand and contract as they absorb and emit radiation, causing them to pulsate in a predictable pattern. This behavior, discovered in 1912 by astronomer Henrietta Swan Leavitt, allows astronomers to determine the absolute brightness of these stars, which can then be used to measure their distances. This Cepheid-based technique, known as the cosmic distance ladder, was a groundbreaking discovery that allowed astronomers to measure vast distances. The first rung of the ladder is constructed by measuring nearby Cepheids and cross-checking their distances. From this, the distances of more distant stars and galaxies are determined by observing how much their light has been stretched, redshifted, as the universe expands. By comparing this data, cosmologists can calculate the Hubble constant. In 2019, Rees and his team used this method by pointing the Hubble Space Telescope at the Milky Way's nearest neighbor, the Large Magellanic Cloud. Their results were striking, showing a much higher expansion rate of 74 kilometers per second per megaparsec compared to the Planck measurements. However, Planck's results were limited by its lack of precision in crowded regions of space where distant Cepheids overlapped with neighboring stars. Some skeptical astronomers argued that this discrepancy could have been caused by measurement errors. When the James Webb Space Telescope launched in December 2021, it was expected to resolve or perhaps confirm this divergence. With its 6.5-meter wide mirror, more than 3 times the size of Hubble's, and superior infrared capabilities, James Webb could observe fainter objects and detect a broader range of wavelengths. In a study comparing Cepheids in the galaxy NGC 4258 to supernovae, Rees and his team found results nearly identical to their previous work, 73 kilometers per second per megaparsec. Other measurements, including those by Wendy Friedman using the Hubble Space Telescope and gravitational lensing techniques, returned similar results of 69.6 and 66.6 kilometers per second per megaparsec, respectively. Explanations for the discrepancy vary. Some suggest measurement errors. Others propose new physical phenomena or a combination of both. Rees acknowledges that a significant portion of the data points to the necessity for new physics to address the Hubble tension. Despite its challenges, this tension has sparked exciting debates in the field of cosmology. If resolved, it could lead to groundbreaking discoveries about the nature of dark matter, dark energy, and the fundamental laws governing the universe. It also underscores the importance of continued exploration and the need for increasingly precise instruments like the James Webb Space Telescope. Ultimately, this puzzle reminds us that our understanding of the cosmos is still incomplete. As new observations emerge, they will undoubtedly challenge and refine our existing models, bringing us closer to unraveling the mysteries of the universe. Actual science posits that the primary hypothesis is that dark energy's conduct has changed over time. If dark energy was once stronger and then gradually faded, it would make the universe appear smaller in its earlier stages, resulting in a faster expansion rate today. Various possibilities include the presence of two types of dark energy or dark matter interacting with light. However, these theories present complexities that many cosmologists are hesitant to embrace without further evidence. James Webb's revelations are not simply testing our understanding of dark energy and dark matter. They are reshaping our ideas about universe evolution. By looking further back in time than ever before, the telescope has revealed galaxies that were significantly more massive and advanced than the standard model had predicted, forming just a short time after the Big Bang. Early systems, which should have been composed of young, hot stars, were found to contain heavy elements and even extremely massive black holes at their centers, features that challenge the traditional model of universe development. These discoveries have intensified debates within cosmology, suggesting that the processes governing galaxy formation may have been more rapid and efficient than previously thought. In addition to addressing these profound mysteries, James Webb's findings have further deepened the enigma surrounding dark matter and dark energy. Despite being the dominant components of the universe, both remain poorly understood. While dark matter interacts gravitationally, its exact nature is still unclear, prompting ongoing research into its detection. Similarly, dark energy drives the accelerated expansion of the universe. However, discrepancies like the Hubble tension raise the possibility that dark energy properties are not uniform across spacetime. Alternative theories suggest dynamic forms of dark energy that could evolve over time, affecting the expansion rate differently at various stages of the universe's history. To address these mysteries, cosmologists will need advanced observational tools like the James Webb Space Telescope and theoretical frameworks that can integrate the new data without discarding the successes of current models. The implications of Webb's discoveries extend far beyond cosmology, impacting broader astrophysical inquiries, including the origins of life and the conditions necessary for life to arise on other planets. By examining distant galaxies, astronomers hope to uncover clues about how Earth-like planets might form around other stars, offering potential insights into the prevalence and diversity of life in the universe. Looking ahead, the James Webb Space Telescope promises to continue pushing the boundaries of our cosmic understanding. Its unparalleled sensitivity and resolution enable astronomers to study the atmospheres of exoplanets, map galaxies more precisely, and examine the earliest epochs of cosmic history with unmatched accuracy. These efforts will not only expand our understanding of the universe's past, but also pave the way for groundbreaking discoveries that could transform our perception of physics, cosmology, and our place in the universe. As Webb enters its operational stage, cosmologists eagerly anticipate the new insights that will emerge. Whether unraveling the mysteries of dark matter and dark energy, understanding galaxy formation, or searching for life beyond Earth, the telescope stands at the forefront, poised to revolutionize our view of the universe in unimaginable ways. In conclusion, the intersection of cutting-edge technology, theoretical innovation, and precise observation heralds an exciting new era for cosmology and astronomy. James Webb's contributions are set to play a pivotal role in refining our understanding of the universe's origins and evolution, challenging established theories while opening doors to remarkable discoveries. As we venture further into this exploration, the secrets of the universe await, with the James Webb Space Telescope leading the way in uncovering the mysteries of our vast cosmic heritage and future. The impact of the James Webb Space Telescope, JWST, goes beyond measuring the expansion of the universe or revealing the details of early galaxies. It is also poised to address some of the most profound questions in cosmology. That our current understanding of the universe might be flawed is not a new idea, but the precision of JWST observations has brought this possibility into sharp focus. This includes understanding the behavior of dark matter and dark energy, which are critical to the universe's large-scale structure, but remain elusive. One of the most exciting aspects of JWST lies in its ability to study the early universe in ways that previous telescopes, such as Hubble, could not. With its ability to capture light from galaxies formed just 300 million years after the Big Bang, JWST is providing insights into the initial stages of galaxy formation. The presence of massive, mature galaxies at such an early stage of the universe challenges the traditional theory that galaxies should have taken longer to form. This raises the possibility that some processes, such as star formation or black hole growth, may have been far more efficient in the early universe than previously thought. Additionally, these surprising findings have implications not only for galaxy formation, but also for understanding the role of dark matter in shaping the universe's structure. Dark matter is believed to have played a critical role in the formation of galaxies by exerting gravitational forces, yet its exact nature remains a mystery. JWST observations could help illuminate how dark matter influenced galaxy formation, potentially revealing new properties of this elusive substance. In addition to dark matter, JWST is also advancing the study of exoplanets and the conditions necessary for life beyond Earth. One of the telescope's primary missions is to analyze the atmospheres of distant exoplanets, searching for signs that could indicate habitability or even life. By studying the chemical composition of exoplanetary atmospheres, scientists hope to uncover the conditions under which life could arise elsewhere in the universe. These findings could provide valuable insights into whether Earth-like conditions are rare or common in the cosmos. As we delve deeper into the data from JWST, it is becoming increasingly clear that we are on the brink of discovering new physics. Whether it's the evolving nature of dark energy, the surprising complexity of early galaxies, or the elusive behavior of dark matter, JWST is opening up new avenues for understanding the universe. It is not only refining our current theories but also challenging them, forcing scientists to think in new ways and consider the possibility that some of our most fundamental assumptions may need to be reconsidered. These discoveries are advancing our knowledge of cosmology while also pushing the boundaries of particle physics, astronomy, and even philosophy. As we continue to explore the universe through the lens of JWST, we are not just learning about stars and galaxies. We are gaining a deeper understanding of the very laws of physics that govern our reality. The questions raised by JWST's discoveries could lead to a paradigm shift in our understanding of the universe's origin. The paradigm shift triggered by the James Webb Space Telescope, JWST, is likely to influence not only cosmology, but also our understanding of fundamental physics. By unveiling evidence that challenges current models, the telescope is encouraging researchers to consider new theories that could bridge gaps in our knowledge. One of the most significant areas under scrutiny is the nature of dark energy. While the standard model suggests that dark energy is a constant force driving the universe's accelerated expansion, the new observations hint at a more dynamic behavior. If dark energy evolves over time, it could fundamentally alter our understanding of the universe's past and future. Similarly, the anomalies observed in galaxy formation and evolution suggest that our understanding of dark matter's role may be incomplete. Dark matter is thought to serve as the gravitational scaffolding for galaxy formation. Yet the discovery of massive galaxies so early in cosmic history raises questions about how these structures could have formed so quickly. The potential for new physics extends beyond cosmology. JWST's ability to study exoplanetary atmospheres in unprecedented detail could have profound implications for astrobiology. By identifying the chemical fingerprints of elements like oxygen, methane, or water vapor, JWST may uncover evidence of life on other planets or determine the conditions that make life possible. Furthermore, the telescope's insights into star and planet formation are shedding light on processes that govern the birth of planetary systems. Understanding how stars and planets form could provide clues about the factors that lead to the emergence of habitable worlds. As JWST continues to gather data, its discoveries are likely to inspire new generations of scientists to tackle the questions it raises. The telescope's findings highlight the interconnectedness of different scientific fields, from particle physics to planetary science, emphasizing that progress in one area often leads to breakthroughs in others. In the coming decades, the data collected by JWST will serve as a cornerstone for scientific research. Future telescopes, both ground-based and space-based, will build upon its discoveries, further enhancing our understanding of the cosmos. Ultimately, The James Webb Space Telescope represents a transformative leap forward in our quest to understand the universe. Its findings remind us of the vastness of the unknown and the boundless potential of human curiosity and ingenuity. As we continue to explore the cosmos, the knowledge gained from JWST will serve as a guide, helping us navigate the mysteries of the universe and our place within it. The questions it raises may take decades, or even centuries, to answer, but they also ensure that the pursuit of knowledge remains an enduring and inspiring endeavor.